Good morning, students. Today we are going to discuss few numericals on motional EMF. So this is related with chapter number 6, electromagnetic induction. These numericals are very important for the board examination. Now this is the first question. A metallic rod of length L is rotated with angular velocity of omega with one end hanged at the center and the other end at the circumference of circular metallic ring of radius L about an axis passing through the center and perpendicular to the plane of ring. A constant uniform magnetic field B parallel to the axis is present everywhere. Deduce an expression for EMF between the center and the circular metallic ring. Means this is the metallic ring of radius L and a wire of length capital L is fixed at center, and this rod is rotating over the circumference of the metallic wire. Now we have to calculate the EMF, right? So we have to calculate the expression for EMF. Now you can see there is a magnetic field which is perpendicular to the plane. Parallel to the axis means perpendicular to the plane. When a metallic rod or metal moves in a magnetic field, so the motional EMF will produce. Now we are going to calculate the thing. To calculate the induced EMF, first we have to find the change in flux, change in magnetic flux, right? Now see, the angular velocity of the rod will be 2 pi by capital T, right? So this is the omega. Now what will be the time period? Its time period will be capital T, right? Now if the rod is complete one revolution, so what will be the change in flux? Magnetic field into area coverage, right? So this is phi. Okay. Now area means the area covered by this rod. So that will be the area of the metallic ring. That will be pi L, capital L square. Now as per the Faraday law, the induced EMF equal to time rate of change of flux. This is the flux and the time taken in a one revolution is capital T. So we can write it B pi L square by capital T. Now substitute the value of capital T. Capital T is nothing but the time period. So from this expression we can write it as 2 pi by omega. Now the final expression will be E equal to half B omega L square. So this is the induced EMF, right? So this is the expression for induced EMF. Now this is question number 2. A jet traveling towards west with the speed 1800 km per hour. What is the voltage difference produced between the ends of the wings having the span of 25 meters? If the earth magnetic field is located of the location is of magnitude 5 into 10 to the power minus 4 Tesla, the dip angle is 30 degrees. Now this is the magnetic field and this is the dip angle, right? This is earth magnetic field 5 into 10 to the power minus 40. Since the jet is going towards the west, so the perpendicular magnetic field will be the vertical component of the magnetic field, and the vertical component of magnetic field will be VB is equal to B sin theta. And what is B? B is 5 into 10 to the power minus 4. And what is theta? That is 30 degrees. So we are taking this vertical component as magnetic field. Now the motional, first of all we have to write the given. Convert kilometer per hour into meter per second, means in SI system. Length is 25 meter. Magnetic field intensity capital B of earth magnetic field is 5 into 10 to the power minus 4, and the theta means the angle of dip is 30 degree. So the motional EMF will be VV, this is the vertical component, means B sin theta, into V into L. Now substitute the value, this is B, this is sin theta. V means velocity is 500 meter per second and 25 is the length. Now calculate, after multiplying all these factors we will get 3.1 volt is the motional EMF. Now this is the third question. A conducting rod PQ of length L is connected to a resistor R, is moved at a uniform speed V, normal to the magnetic field capital V, given in the figure. Now what is figure? This is the figure. Now this is the rod and it is connected with the resistor and it is moving with uniform speed in a magnetic field. This is the region of magnetic field, right? Now what will happen if the conductor will move? The induced EMF will produce, and since it is connected with the resistor, so induced current will also flow in this circuit. Now what we have to calculate? Deduce the expression for induced EMF. Number 2, find the force required to move the rod in the magnetic field. And third one, to find the direction of induced current. Now students see, when the rod will move, it will cut the magnetic flux. So before calculating the EMF, we have to find the change in magnetic flux. Now time rate of change of magnetic flux is EMF. So what we have to do, first of all we have to calculate the change in flux. And change in flux is nothing but a B, magnetic field into area. Now area covered by this rod in delta t time is delta x. This is the length, right? So this is magnetic flux. Now we have to apply the Faraday law, d phi by dt. It means we have to divide this expression by dt. So we will get E equal to BLV. So this is the induced EMF or motional EMF, BLV. Now what will be the force? If there is a induced EMF, since it is connected with this rod, the current will be there. Now what will be the current? Current will be E by R. E is induced EMF BLV divided by R. Now this current carrying rod is moving in the magnetic field, right? So every current carrying conductor in magnetic field experiences the force, and that force is ILB. This is L. ILB sin theta. Now theta is a 90 degree. Reason is that magnetic field is in inward direction. So, and this is the current element. So angle between the current element and the magnetic field is 90 degree. So sin 90 is 1. Now we have to put the value of I, current. So this is BLV by R into IB. Now after multiplying the factor, we will get B square L square V divided by R. This is the force. Now the last one is direction of induced EMF. See what is happening. A current carrying wire moving in a magnetic field, it is experiencing the force, right? Now we have to pull it against the force, right? So as per the Fleming's left hand rule, the direction of current will be anti-clockwise in the circuit, right? Now the today's last question, the current flowing through an inductor with self-inductance L continuously increasing. Right? The current is continuously increasing. Now plot the graph between magnetic flux and current. Now student, you know that flux is directly proportional to current. If flux is directly proportional to current, it means there will be the straight line. But that straight line should not be parallel to the x-axis or y-axis. Means it is the some sort of slope will be there. Right? Second case, the induced EMF versus di by dt. Now you can see, as per the Faraday law, E is equal to minus d phi by dt. And what is phi? Li from this expression, Li. After substituting the value Li over here, L is a constant quantity, so it can be written as minus L di by dt. Now E is directly proportional to di by dt. Right? If we will draw this graph, so this graph will be like this. Now third one, the magnetic potential energy, this is U equal to half Li square. Now this is like a parabola. Right? So the graph will be like this. Right? So the graph will be like this. This is the parabolic and the symmetry along y-axis. So this is all about of today's lecture. Thank you very much.